thanks for the organizer, Professor Gu, for giving me opportunity to give a colloquial talk. And actually, I completely agree with the comments on Professor Gu. And while I'm preparing this talk, this is a very colloquial introductory survey of several areas. So for some part, I'm not an expert. Actually, I'm quite away from this, some part of this talk. But while I'm preparing this one, I learned a lot. So, but even if I'm not going to present in full detail, but this gave me a very good opportunity to investigate some other area. Okay, so today's the keywords is the soliton and dispersive equation. Okay, so probably you might have heard about the soliton at least once. Okay, so soliton is very the important notion in the field theory, the mostly classical and quantum field theory in physics, and then it appears everywhere in field theory or something connected to superconductor or okay. So basically at the beginning of the talk, I'm going to present some history of the discovery of the soliton, and then because even if the soliton soliton appeared in a lot of the area, I'm going to restrict to very simple case, very classical example of the soliton, which is a soliton in KdV equations. Okay. Okay. So let's read the definition of the solitons. So basically, there is no precise definition for the soliton solution. Soliton is a form of the special type of the solution to some evolution equation. So here, evolution equation means time-dependent equation. Okay. But as time is evolve, but the soliton solution doesn't change its time, its form. So the solution which is a wave with a permanent form. Okay? And then also it is localized in space. So basically, in the picture that you can think just a single wave. But this may propagate, or the phase of this may change, but it is localized in space, and then it should decay to zero or to some constant as x goes to infinity. Okay? And so if first two conditions satisfied, the people call the wave is a solitary wave because it has just only one wave. But if the third condition is satisfied, then people call that is a soliton. So here, something tone on means is some kind of particle character. Okay, so basically the soliton solutions can interact with other soliton, but after collision, two soliton they retain their form with unchanged. Okay, so that means that the third character is actually represent a particle like the character of the soliton, because even if this soliton solution is actually from some sort of a wave equation, like a nonlinear wave equation, but the soliton solution behave more like a particle. So when we write out the physical theory, in classical or quantum field theory, everything is wave in here. Everything is a continuous field. But even if this is a continuous field, we want to describe something like a particle. Okay, and then the particle, when they even if they collide, they don't change too much. They may lose some mass, or they may lose if the collision is not elastic, then they may emit some sort of radiation. But we still have a very stable the property among the collision. Okay? But in this talk, we are going to restrict our attention to the dispersive equation, and then mostly I'm going to talk with the example of KdV equations. Okay, so this is basically history of the KdV equation and the soliton of the KdV equation. So in 1834, he's not a mathematician, he's just a person. He observed a solitary wave from the narrow canal. So in Scotland, but so in a narrow canal, then what he observed is actually water wave equation. In the water wave, in some situation, there is a solitary wave just to translate without changing its form. Okay? So in his note, he described, he made several experiments in that canal. So he found, by observation, he just found what is the relation between the speed of the soliton and the height of the soliton, or the gravity and some sort of the width of the soliton. Okay? So he made a very precise note on here. Okay? So his observation posed a very important question, that whether the water wave equation would possess such a solitary wave. Okay? At this time, the Navier-Stokes equation, or the Euler equation, they're describing the incompressible fluid, which is water, is already known. And then people know what is the water wave equation. What is the equation that's describing the water surface wave. Okay? But because the water wave equation itself is very complicated, it is, at that time it is impossible to solve it. But by approximating to some reason, the people ask if they can derive some sort of approximate equation possessing admitting the solitary wave. Okay? So that problem is solved by Korteweg and Debris in 1895. They derive a nonlinear equation later that is called the KDB equations, and then governing the long surface wave. Okay? So in the water wave, they look at some range when the wavelength is very large, but the amplitude of the wave is very small. In such an approximation, they can derive they can simplify water wave equation to derive KDB equation. Okay? And then for this equation, they also show that there exists a Soliton solution. They derive explicit formula for the Soliton solution, which we'll see a little bit later. And then in 1960s, there are a number of applications of the water wave, the KDB equation appeared in modern physics. This is just some sort of example, so collected from the literature. So actually, I don't know what it is exactly, but the KDB equation is not only from the water wave approximation, it is from the many physical settings. And okay, very interesting, the numerical experiment was done by Kruskal and Zabsky in 1965. What they performed is, okay, so in Russell's period, they already observed that the soliton, this solitary wave is very stable against the collision. Okay? Then but the Kruskal and Zabsky actually they conducted a numerical experiment to check if the solitary wave is stable under collision. Okay? So they checked that actually the solitary wave, they retain their form even after the interaction, after the collision. Okay? So from that time that they call that solitary wave is a soliton to emphasize its particle-like character. And then the couple of years later, so a breakthrough is made by the four people, Gardner Green, Kruskal, Mira. Then they, in fact, discovered very nice, very amazing the method inverse scattering transform for the KDB equation. So by the inverse scattering transformation, they were able to solve that nonlinear problem. They were able to solve that nonlinear problem just by decomposing into some sort of linear problems. Okay. So I'm going to revisit what is the inverse scattering transformation. And 2 years later, Peter Lax generalized their idea, and then he reformulated the inverse scattering transformation as a Lax pair. Okay? So he looked at some sort of equation of the operator, applying to some function instead of looking at the function itself. So after Lax pair appeared, the inverse scattering transformation got much simpler. Okay, originally inverse scattering transform looked very ugly, very complicated. So it seems it is impossible that to apply some other equation. But Larkspur is very simple. So from his work, the many other the integrable equation was found. For instance, 1D nonlinear Schrödinger equation or Kamasa-Holm equation, or KP equation. There are so many integrable equations that satisfy this structure. Okay. So after the four people's work and the Lark's work, this integrable system became a very fascinating area by the geometer and physicists, but not by analysts. Okay, so we became interested such a soliton behavior on from 1980s. Okay, so to explain how we can get the soliton solution, we need to explain. We need to look at some elementary property of the dispersive equation. Okay, so dispersive equation is a class of the partial differential equation, but this doesn't belong to any of the main category, like hyperbolic or parabolic or elliptic. Okay, so this is a class. This class is defined by some sort of behavior of the wave. Okay, so we're going to call a differential equation is dispersive if different frequencies propagate at different speed. Okay, so there are more the precise the definition for the dispersive equation. So if the linear part of the equation is written in this form, then we're going to call it a dispersive equation. Okay, so here the p is just a polynomial, and then d is a derivative, but not the usual derivative over I. So from Fourier transform, you know that the Fourier transform of the derivative is in fact I times psi, I times the frequency. Okay, so but here because we divide by I, so d of f is the same as psi of this. Okay, for simplicity, though, we just discard I. We divide by I. Okay, then but we need one I here. And there are many examples of dispersive equation, and those four are the most intensively studied dispersive equation. One is, and they are all linear. One is the Schrödinger equations. So here you see the Laplacian, and then you see you can see that from Fourier transformation, the Fourier multiplier of the Laplacian is just negative psi square. So that's why we need I in one other side. Or for the Airy equation, we have three derivatives, but three usual derivatives means I psi to the cube. That means negative I to the negative I times psi cube. So actually this also satisfies this condition. Okay, and wave equation or the Klein-Gordon equation is also satisfy that condition in the same way. Okay? So here the polynomial is a cubic polynomial x to the cube, and this is x squared. Okay, so this is the linear equation, and for such a linear equation, though we can, by taking Fourier transformation and evolving in time in Fourier space, and then taking inverse Fourier transformation, we can find out explicit formula for the linear dispersive equation. The formula is written in this form. So here, so you can, for instance, for the Airy equation, you can think the p of psi is just the psi cube. Okay? And then we're going to write that this is a linear equation in this form. Okay? Then such the linear dispersive equation has many common identity. One is the mass conservation. Okay? So L2 mass just conserved because the Fourier multiplier of the linear solution is unitary. It's just one if you take the after value. So this operator is actually a unitary operator. And then the second one is a dispersionist way. Okay? So at infinity norm of the solution, as time goes, it should decay to zero. Okay, if the initial data is just the case. So it is because, say, originally we can think on initial data it is a superposition of high frequency data and low frequency data. But in the solution to dispersive equation, high frequency data move very fast, and the low frequency data it moves slower. So later in time, high frequency data located here, low frequency data is here. Okay? So by such a decomposition in space, we can expect that the decrease of in at infinity or at any LP node p greater than 2. Okay? So this is a very important main property of the dispersive equation. Okay? So even if they decay to 0, but it is quite different from the diffusive equation, like a solution to heat equation, because we have some sort of conservation law. So that means mass is something is conserved, but they distribute more widely. So that's why if you look at just some local region, we can observe that the amplitude is small. It's getting smaller. Okay? So by using the dispersive equation and some harmonic analysis, we can also derive a Strickhardt estimate, and then for last 2 decades, Strickhardt estimate played a very crucial role in the theory of this dispersive equation. But in today's talk, we are not going to discuss that. But in particular, by observing the dispersive equation, we can easily conclude that actually linear equation doesn't admit the Soliton solution, because the Soliton solution should pertain a permanent form, but the at infinity norm height of the solution should decay for the linear solution. So there is no Soliton for the linear equation. Okay? Soliton solution can appear only when you have nonlinear terms. Okay? So more interestingly, we study nonlinear dispersive equation, and we just added 2 nonlinear terms for the linear part of the equation. So this is a nonlinear Schrödinger equation, and the second one is a generalized KdV equation. When P, in the GKdV, when P is 2, that is the usual KdV equation, and P is 3 is modified KdV, and for other P, that is just called the generalized KdV equation. Okay? But so we just add that such a nonlinear term, and the nonlinear term may play some role to form a Soliton solutions. Okay? But there are 2 types of the nonlinear term. So one is a focusing case, or the other is a defocusing case. Okay? So actually, the linear part, the linear equation, the linear dispersion part, just try to spread out the solution. Okay? But if the nonlinear effect try to attract reinforce the solution to the center, then there would be several scenario. If the nonlinear effect is bigger than the linear dispersion effect, then the solution may blow a finite time blow. Or even if we have a reinforcing effect, if the spreading out, the dispersion effect is bigger, then we can still expect the global solution, and then with the dispersion. Okay? But soliton is exactly the balance between nonlinear reinforcing nonlinear effect and dispersion effect. Okay? So when those 2 effects make some ejective balance, then we can expect some sort of balance. You can see that actually the soliton solution, they doesn't attract any longer, but they don't disperse. Okay, so we can understand soliton is as a balance of between nonlinear reinforcing nonlinear effect and dispersion. Okay, so this is the focusing case when the sign of the nonlinearity is -1 for the nonlinear Schrödinger equation. But if the sign is different, then this nonlinear term is also the play a recursive, give a recursive effect. So that means actually such a recursive nonlinear effect that boosts the dispersion. Okay, so by the effect, the solutions try to spread out, but we just added the add some the same kind of effect by the nonlinear term. So for the defocusing case, we don't expect such a soliton solutions or finite envelope. We just expect just one single scenario, the solution, the disperse as a linear solution. Okay, so the L infinity norm of the solution should decay to 0. So there is no, there is only one scenario for the defocusing equation, but there are a lot of these several scenarios for the focusing cases. But because our topic here is a soliton solution, I'm going to look at the focusing cases. And then, so we're going to derive the soliton solution. Okay. Okay, then, now, let's try to find out the soliton solution for the KDV or NLS. So, because from the definition of the soliton solution, the each may propagate with speed c, but the form of the solution shouldn't change. Okay, so we're going to plug in this answer q, the utx is qx minus ct into the original KDV equation. Or for the NLS, we're going to put in this answer. Okay, so here it doesn't propagate; it just stays physically. But the phase of actually the solution to the NLF is complex valued, but the solution to the KDV is real valued. So the phase of this NLS solution may change. Okay, if you just plug in this answer to the equation, then Q should satisfy this. Okay, so this is a simple case when C or lambda is 1. Okay, so if there exists some sort of good solution to these elliptic equations, then that gives us a soliton solution to KDV or NLS. Okay, so this is a quite elliptic problem, and then it is almost solved in 1980s and by a lot of people. And then still some analog of such a problem is still studied. Okay, for instance, in Korea, in post-tech, the Professor Jae-young Byun or the Youngnan Lee in Seogang University, they working on this kind of equations with some hard nonlinearity. Okay, so here, so this elliptic equation, they admitted a lot of solutions, but among such solutions, we are interested in a ground state. Okay, so basically, this is an Euler-Lagrange equation of some functional, and then the minimizer of the functional is satisfy that Euler-Lagrange equation. Okay, and then that equation, that solution satisfies such a condition. Q is the positive, and then the value of the functional of this solution is minimal, is smallest, because that is minimizer. Okay, and then so many people contributed to this, and then they showed there exists a ground state solution, so satisfying those three conditions, which is positive, and then spherically symmetric, and then decay exponentially for this particular case. Okay, and then this is such a the ground state solution exists when the p is less than some number. Okay, and I was pleased to see a note by the Terry Tao about the Fields medal and some medalists of this the ICM. That one of the or the recipient, Louis Remberg. So actually, he contributed the second piece, the spherically symmetric case. Okay. Spherically symmetric. So Q is in fact. So X is in Rn, but Q is the same as Q of R. So it depends only on that is a radial function. Okay. R is so R and omega. but it depends only on the radial, the variable. Okay? That is the cool. Yes.
So you second generalize the KGB equation.
Yeah.
What is the value left-hand side?
Oh, I'm sorry. That was a typo. This is the time derivative of u. Okay. Okay. So to show the spherical symmetric, the Louis-Nirenberg and the Gidas, then they invented an application of maximal principle, which is called the moving frame method, and then using that, they were able to show this one. Okay, that was a digression. Okay, in one-dimensional case, so this is such a thing. It is solved for any dimension, but when dimension is greater than or equal to 2, then we don't know what is the exact formula for this. But one-dimensional case, this is a simple ODE, second order ODE, and then originally the Korteweg and De Vries, they found such a formula for the solution. And then you can find out there's such a formula from graduate PD text, like advanced. Okay? So from here, you can observe that actually this is symmetric. So even function, because this is one-dimensional case, and then Cauchy function is even function, and this is the Cauchy function is exponential function basically. So it is a decaying exponential. Okay, so once you find out the ground state, and we have you find the Soliton solution. Okay, then first question about the Soliton solution is just stability. Okay, so but here we can obtain the weaker sense of the stability. So let me explain a bit later. And then the statement goes in this way. So initially, if the initial data is very close to the soliton, exactly, if the initial data is exactly soliton, then it's just propagate, right? But now we're going to make some perturbation of the soliton, right? There are some noise on the soliton. Then for all time, the solution should stay close to the soliton solution. That is the notion of the stability. Okay. Then now let me explain why this is called orbital stability. So now let's say this is a solution, a soliton solution with speed 1. Okay. And then if you have another little bit different soliton solution with speed 1.001, then they are very close, right? So initially, the distance between the two difference between the two solutions is very small. But as time goes, this propagate with speed 1, but this propagate with speed 1.001. But if time goes after a long time, one solution stay here, and then the other solution stay here, and the distance between two solutions should be 0.001 times the time. Okay, so for the long time, we don't expect a conventional notion of the stability because of this. So but if you look at this, the form of the solution doesn't change. They look very similar still, but the location is different. So if we just move one solution to the other and they overlap, then the difference between two solutions is still very small, right? That is a notion of the orbital stability. Okay? So here, we can allow a translation and then take the infimum. Okay? Then we can get it is small. Okay? For the NLS, that is a little bit more complicated, but in the same manner. So we have to translate, and we also have to the change each phase. Okay? So and then we take the minimum over the phase change and the translation. Okay? Then this is true. Okay? This orbital stability is intensively studied, not only for this equation. Any equation admits the soliton. Okay? So once we know there is a soliton solution, then the people just automatically study if the orbital stability is true. So today, for curiosity, I just search the MassINet with the title, the keyword in the title, orbital stability. Then I was able to find out more than 100 papers just with this title. Okay, but it is originated by the Benjamin in 1975. He solved the case, the simplest case, the KDB case. And then the breakthrough is made by the Weinstein in 1986. He introduces very simple, nice method, the Lyapunov functional method. This is very similar to the second differential method in ODE when they show the stability. Okay? So basically, the method of the Lyapunov functional method, Lyapunov functional is kind of a conservation law of the equation. And then this energy and mass both are conservation law, so linear combination is also conservation law to the equation. So this doesn't change in time. Okay? But by some computation, we can check the Soliton solution is in fact the critical point of this functional. So here we take the Fresher derivative over the functional, and then if in ODE, if we have some sort of equilibrium like a critical point, then we can check its stability by taking second derivative. Okay, so we take the second Fresher derivative of this functional, and then that is positive all direction except just one direction. Okay, so that the exception is translation, because if we translate, it is still soliton, so we don't expect it is strictly positive. The second derivative of this is positive when we just when we make a derivative to the generator of the translation. Okay. Okay, so by this argument, the orbital stability of KDB, NLS, or S is almost done. Okay. Then now the further in particular KDB equations, we have a better than orbital stability, which is asymptotic stability. Okay. So in ODE, so different is if the initial data when this is small, then this is also small. Then that implies the stability. But asymptotic stability means if this is small, then difference is asymptotically going to zero. So asymptotic stability is a stronger condition than stability. Okay? But for some reason, for the KDB equations, we have asymptotic stability. Okay? It is very recently done in 2002. So then there are very simple the heuristic argument to show that why this soliton should satisfy asymptotic stability. So just trying to plane a wave to the linear area equations, then that wave number that should be crystal cube. So we can derive the planar wave solution in this form. Then in view of the phase velocity, we can observe that phase velocity is a negative c squared. So that means the solution to the linear equation should propagate to the negative c with the speed with negative c squared, which means it propagates to the left. Okay, but from the Soliton solution, we know that c is positive, right? So speed of the Soliton solution is positive. That means Soliton move to the right. Okay, so initially, if we have a Soliton solution with some noise, some perturbation. Okay, then as time goes, this soliton should move to here, but other noise should move to the other direction. So later in time, so we can expect solution look like with some noise. Okay? So if you look at just the region around the soliton, then we can observe that soliton is getting cleaner and cleaner. Okay? So this denoising effect is called is described as asymptotic stability. So the statement will look like this. For if the initial data close to the Q, then asymptotically it should go to 0. Okay. I missed one. Yeah, I think I missed one slide.
잠깐 질문이.
Yeah.
아까 사이가 크게 관계 없나요?
크게 관계가 있죠.
사이즈 관계가 좀 무조건 이렇게 크면 된다.
그러니까 이게 이 하이 프리퀀시는 더 빨리 가고 그 로우 프리퀀시는 천천히 가지만 마이너스 크 사이 스퀘어니까 방향은 항상 이 방향입니다.
그러니까
예.
사이즈 관계가 좀 크면 된다.
예, 예.
그러니까 그게 빠르면 금방 크면 된다.
그렇죠. Actually, I made a mistake. I skipped the mistake of putting the button at the one slide. So, so I need to introduce some important fact about the KDV equations before we discuss the asymptotic stability. Okay. So this is a KDV equation. So in the introduction, as I explained, it is arising from the water wave, some model, and then later we are going to see it is the completely integrable, and then it has the first two, the conservation laws. But in this slide, what is important is the last two, scaling invariance and Soliton solutions. Okay, so for any solution, so if UTX is a solution to the KDV equation, then U of C of TX is also solution. Okay, C is a positive number. It is a rescaled solution. Okay, so because every term is homogeneous, and then just applying this into the equation, then you can check that this also satisfies the equation. So this is a scaling invariance. And so previously we already found the solution, the Soliton solution Q x minus t when C is 1. Right? So which is a Soliton solution moving with speed 1. Okay? Then by this scaling invariance, we can find out the solution, Soliton solution, moving arbitrary speed c. Okay, so this is the actual Q sub c, and then this is a Soliton solution moving with speed c. Okay, then what is the important in this? If c is small, then from this scaling property, then the solution is wider, and it is shorter. C is small. But if C is big, then solution is very tall and thin. Okay. Yeah.
Look at the equation, KDV equation.
Yeah.
Instead of 2, you replace by 3.
It doesn't matter. All the same equation by scaling. Yeah. So for instance, if you replace u by u over 2, then we can remove the number 2. Okay. Or the sign in front of the equation is also not important. By choosing u of x, we replace u of negative x t or u of x negative t. Yeah. No, because in the original definition, I wrote the in general u square sub x. I wrote nonlinear term in general in this form, so that's why I choose 2. But the historically, if you look at the literature, then they use usually this is 6 for some reason. Okay, but it is mathematically it is nothing, not important. Okay, so So small soliton is wider, but it is moving slower. The short big soliton, when C is big, it is moving faster. And then you can also see the mass of each soliton for the speed C. So soliton with speed C is actually this size. Okay, so that means if the faster soliton is bigger, taller but thinner, but the slower soliton with a small velocity is wider but very shorter, and then also small in mass.
아까 그 솔리톤이 말이죠. 폼이 안 변한다고 그랬잖아요.
예.
근데 웨이브에는 그러면 여러 개 솔리톤을 같이 움직이는
예, 그렇죠.
거기에 계속 거기에 간다 이렇게.
예.
아 그럼 그 웨이브에서 그 솔리톤이 말이지 그 C가 보통
예.
그 웨이브 전에 C가 어느 범위에서 이렇게 결합이 됩니까? 그럼 C에 따라서 얼마든지
그러니까 C가 정해지면 그냥 하나의 솔리톤이 정해져 있고 걔는 그냥 계속 그대로 가는 거예요.
근데 우리가 보기에는
예.
그 종합적으로 그 컴포지트가 좀 나타나거든요. C에 여러 가지 C에 대해서.
예, 그렇죠.
근데 속도도 다른 게 분리 안 돼요?
그게 이제 조금 이따 말씀드릴 겁니다.
아, 그래요?
예.
이거 어찌 보면 자꾸 변할 것 같아요. 근데 C가 다 다르니까.
예, 근데 그러면은 스테이블 하지 않죠. C가 막 변하면. 예.
아, 다른 얘기 한다고요?
예. Yeah. So this is another the property of the KDB equation. Okay. So then, as Professor Choi mentioned, so actually usually we can so once we know what just one soliton solution, then we can also consider the multi-soliton solution. Okay? So basically, just a superposition because this is a nonlinear equation, superposition principle fails, but still we hope that if we can consider some kind of the solution asymptotically, which is same as the superposition of the soliton of various sizes. Okay, so if this is satisfied, as t goes to infinity, if a solution is written asymptotically is in sum of soliton in this form, so we're going to call the UTX is multi-soliton solutions. Okay, so that is just a definition. Then, so there are some sort of the asymptotic stability result of the multi-soliton solution when they don't have interaction. Okay, so it is quite easy. So originally the bigger soliton located here on the right, and then smaller soliton and slower soliton located here, right? Then bigger soliton move faster. So as this is a time variable. As time goes, this is moving very fast. But the slower soliton is moving slower. So after a long time, one is located here, then the other is located here. So distance between two solitons is getting bigger. Okay? In this case, we don't expect the interaction between two solitons. They just behave independently. Okay? In this case, we still have asymptotic stability. Okay? So that is this result. But this is not the interesting case because we are more interested when they have some sort of interaction. Okay, so which means at the beginning time, if the bigger soliton located on the right and the slower soliton here, then because this is slow, this is faster, eventually they have to collide. Right? In that case, what happened after the collision? That would be the most interesting question. For the partial answer to this situation is done by the complete integrability. Okay? For the KDB equations, it is originally discovered by the 4 people in 1967. Then afterward, it is intensively studied, and then there are a lot of names is connected to this. One is the originally was an inverse scattering transform, and then Lux pair or bi-Hamiltonian structure, they or nonlinear Fourier transformation. Okay, so actually they are all indicate almost the same object, it's a mathematical subject. Okay, to explain what is this inverse scattering transformation, So it is instructive to look at the linear case. Okay? So this is a undergraduate the PDE course selected from the grade PDE course. For the linear equations, so this is defined on the real line. Then to solve this the partial differential equation, we take the Fourier transform to the x variable. Okay? Then this x partial derivative change to just multiply I psi cube. Then for fixed psi, we have a time derivative. This is a function of t, and then this is also a function of t. And then we have only one time derivative. That means we can understand this is just ODE. So we can evolve in time to find out the solution at time t. And then we take the inverse Fourier transformation to recover original solution. Okay? So that is possible only when the equation is linear, and then the coefficient of each term is a constant, and then the domain of the equation is good. It's a real line or the Euclidean space or torus. Okay? Otherwise, we cannot use such a procedure. Okay? But actually, inverse scattering, inverse scattering or scattering is a nonlinear analog of this. So that's why some people call this is kind of nonlinear Fourier transformation. Okay? So we want to solve this for given initial data, but the initial data should have some sort of condition, so some well-decaying condition. Then we take the direct sum transformation, which corresponds to the Fourier transformation in the linear setting. Okay? And then with the scattering data, then we can evolve in time, and then so actually this is those are eigenvalue or the coefficient of the scattering data at time 0. And then we can evolve in time by solving some sort of ODE. And then the third step is taking inverse scattering. Okay, so as the inverse Fourier transformation. But in the linear case, Fourier transformation and inverse Fourier transformation are essentially same. But in the nonlinear case, taking inverse scattering is quite non-trivial. Okay? So direct scattering problem is known for a while from the time of the discovery of the quantum mechanics, but the inverse scattering was not possible in most applications. It requires very very special the algebraic structure of the equation. Okay? So that's why this became a representative name of this argument. Okay? So, but those three at the step are the linear step. So finding direct scattering or evolving in time, inverse scattering are actually the linear problem, solving some sort of a linear integral equation or linear differential equation. So, but we know how to solve the linear equation. Or in other words, we know solution exists for the linear problem. Okay? So from the procedure, we can solve such a nonlinear problem. Okay? That is a... Oh yeah, this is S lambda t. Thank you. Okay, so but what we are interested in is not how to take inverse scattering, the transformation. We are more interested in the result of the inverse scattering. Okay. So now let me summarize some important results about the inverse scattering, or in other words, the complete integrability. One is I think the one of most important thing is because we can decompose that nonlinear problem into the linear problem, for some sort of initial data, we can expect global solution. We can obtain global solution, and global solution asymptotically decoupled into radiation part and multi-soliton part. Okay? So if you just follow how to do such a procedure, then it is quite natural. Okay? That is the most important result for this talk. So that means we begin with just arbitrary initial data. But one can understand this is a superposition of soliton with various the component, various speed, with some radiation data. Okay. Then as time goes, that is decoupled into some of finite number of the soliton and with some radiation. Radiation is a linear solution. Okay, so the reason why the biggest soliton located on the right is eventually after their interaction, because this is faster, they located on the right, and then smaller soliton. Yes.
아까 그 스캐터링 할 때
예.
항상 됩니까?
예.
스캐터링은 언제든지 돼요?
스캐터링은 그
되고
이니셜 데이터가 뭐 좀 컨디션만 있으면 돼요.
이볼빙 타임도 문제 없고.
예, 그것도 우리.
맨 마지막에
예,
이거 스캐터링이 안 돼요.
예, 예. Okay. So this is the most amazing the result from the complete integrability, and then the more precisely they can find out the explicit formula for the two soliton solutions. Okay, so this is looking complicated, but if you take some asymptotic, then ST goes to infinity or negative infinity, these look like a sum of two solitons. Okay, so that is a result of the complete integrability. Okay.
레디에이션이 없을 때만 되는데 있으면 왜 안 돼요?
레디에이션이 있으면 이 explicit 포뮬라가 쓰여지지 않죠.
근데 또 무슨 매스매티컬이 되게 어려워요? 아니면 피지컬이 문제가?
아니 아무 문제가 없는데요. 이건 그러니까 특수한 경우. 그러니까 보통 일반적으로는 레디에이션하고 그 솔리톤의 썸하고 이렇게 주어지는데 만약에 이니셜 데이터가 만약 이렇게 주어지면 레디에이션이 제로인 경우도 있을 수 있잖아요. 썸은 일반적으로 주어지는. 모양이 정확히 그 처음에 그 솔리톤하고 같죠. 예, 여기서 이 식 펑션이 이게 1 over 코시. 요 솔리톤이요? 그러니까 그
이니셜 모양은 안 되나?
if you look at the asymptotic when t goes to infinity or infinity, then when t is a negative big number, then we have a larger soliton and a smaller soliton here. And then this propagate, this translate faster, but this is slower. At some point they collide, right? And then afterward, the location is exchanged. But here the important fact is the speed of this, which means a parameter of this soliton or this soliton doesn't change. They preserve their parameter.
시간을 이렇게 보내면 솔톤이 다 분리돼 나올 거 아니에요?
예.
그 모양이 나온다고.
예. But when they collide, they look like some sort of this kind of form. Okay, so but the problem is that this work only for the integrable case. Okay, but if we change for the power of the nonlinear term, like when p is not 3 or 2, when p is 4, for instance, for such a generalized KdV equations, we don't know because we don't have the theory, the complete integrability. Okay, but still, so it is natural to ask a question if such a behavior is true for non-integrable case. Okay, so that is a conjecture. Okay, so for generic initial data, so here the meaning of the generic is not well defined. We don't know how generic it is. Okay, so because this is quite vague, the conjecture, and then the global solution is asymptotically decomposed into the multi-soliton plus some radiation error. Okay? That is a big conjecture, but basically we think that this is very far from the current status is very far from the resolution of this. And the integrable case, it is solved by the complete integrability, but still we want to find the analytic proof by the making measure of the norms. Okay? And the non-integrable case is completely open. And 예, 그러니까 그거 조금 이따 보죠. 예. And the orbital stabulary or asymptotic stabulary can be understood as a very first step toward this conjecture. Because in order to solve that problem, to prove such a conjecture, we have to show at least some sort of stabulary of one soliton or multi-soliton. Okay? But it is still very far from the conjecture. Right? So, but analytically, our current status is orbital stabulary, or for some cases, asymptotic stabulary of multi-soliton. And the most interesting, the special case is a collision of the two soliton. Okay, so initially the larger soliton located on the left, and then smaller soliton located here. Then as time goes, then they should collide. Then for the non-integrable case, for instance, when p is 4, so that is for example problem. Then what happened? Okay, so can we expect some sort of the same phenomenon as like integrable equation or not? That is our question. Okay? And then the answer is partially it is right, but not exactly same. Okay. So in 2008, Martin and Moore, they showed. Okay. So and then the answer is done only for very special cases, two extreme cases. When one soliton is just of size 1, and then the other soliton is very small. So size of the soliton is very different. Then they have a result. They still have the similar stabulary of the two soliton structure even after the collision. Okay? But it is not exactly the same situation as integrable case, because it it emits some radiation. Okay? In the integrable case, we begin with the two soliton. After the collision, they result in the two soliton without any radiation. But in the non-integrable case, after the collision, they emit very small radiation, and then originally if the parameter of the soliton is like 1, and this is C, which is very smaller than 1, then parameter of this is a little bit smaller than 1, and then parameter of this is a little bit bigger than this. And then sum of two mass after the collision is a little bit smaller than sum of two mass of this. And then the loss is emitted as a radiation. Okay? So the situation is a tiny different from from the integrable case. So we're going to call this collision is inelastic. Okay? And then, but if you look at the physical situation, when the particles collide, then they create some heat or the sound, and then eventually they lose some sort of energy as an emission, right? So this non-integrable case is more practical, in my opinion.
non-integrable 컨디션이 피직스에서 뭐예요? 아니면 단순히 P 이꼬르 4 뭐 이래가지고.
그러니까 그 complete integrability라는 그 스트럭처가 없을 때를 그냥 non-integrable.
그 피직스로 이게 설명이 잘 안 되니까 요러한 거는 그냥 보나 마나
그 피직스는 그 설명이 안 돼요. 예. 그러니까 피직스에서는 전혀 알 수가 없고, 같은 이퀘이션이라도 코에피션트를 살짝 바꾸면 그게 그냥 non-integrable 되고, 예. 그게 이제 피지시스트도 가장 그 중요한 질문 중에 하나였어요. The second case is another side, the extreme case, when two soliton is almost the same size. So here, the size of the soliton is quite different, but the second case, size of is very similar. This is plus epsilon, this is 1 minus epsilon. Then eventually they have to collide, right? But after they also to lose some sort of mass as a radiation. So there is no pure two soliton solution. So for the non-integrable case, we have only two extreme cases. When two solitons are quite different or in almost the same size. Okay? So the most interesting case is just the general case when size of one is 1 and the other is just 2. Okay? But it is not done yet. Okay? So this is another the later step toward that conjecture, soliton resolution conjecture. So I think those two are the best known result for the to this direction. Okay, so this is one story, and then let me quickly summarize another direction, another approaching to this the soliton resolution conjecture. Okay, so for this, so we consider the nonlinear Schrödinger equation. In the nonlinear Schrödinger equation, we also expect the soliton resolution conjecture. Okay, so for this, the focusing nonlinear Schrödinger equations, then it is not hard to show that the solution eventually decomposed into the 3 pieces. Actually, 2 pieces with error. Okay, this is a little o. One piece is also here the t is missing, so that is typo. One piece is a radiation, which is a linear solution, and then the other piece is a bounded piece. Okay, so we're going to call this is an attractor. Okay. Then, if we show that this attractor is a multi-soliton solution, then that is a resolution of the conjecture. That is a soliton resolution. Okay, so we show that eventually this is a sum of two pieces. One is a linear, the radiation, the dispersing as a linear solution, and the other is a bounded piece. The other is a multi-soliton. Okay, but it's there to dream. So we have our weaker form of the soliton resolution conjecture. Then, so eventually we hope to show the W is a multi-soliton, but we at this time, at this level, we don't know how to prove that, but we can prove very significant property of multi-soliton solution. So the omega satisfy very significant. Make a measure mass just near the center of the soliton. Then the mass of the region mass of the rest of the region that should be very small. So this is exactly that region. Okay. So we just exclude those the center of some sort of the region close to the soliton. Okay. Then t equals 5. So the result is done when t is greater than or equal to 5. Then in the lower dimension, it is technically harder. Yeah, but we can expect the same result, but the tau we can expect, but it is not solved. Okay? So let me quickly explain why this method, the method to prove this is only applicable when t greater than 5. Okay. Okay. So in the rest of the region, the mass should be small. Okay. This happens not only in the frequencies, not only in the physical space. It is also true in the frequency space. We make a cutoff. So very high frequency piece of the L2 mass is also very small. And then what is important is this estimate is independent of the time. Okay, so this should be true for all the time, right? If there is no soliton, then if the solution just dispersed, then originally, even if the data is located, even if the data is here, then eventually they should spread out. Okay, and as time goes, they spread out more widely. Then this cannot be true for arbitrary time. Okay. So for the bounded data, we can show some sort of weaker form of multi-soliton of the soliton resolution. So multi-soliton they obviously satisfy this condition, and then this is some sort of weaker condition than multi-soliton. And then one other the remark about this is actually this condition is equivalent to that functions for all time that is in some sort of compact set, pre-compact set in H1. Okay, so because of time constraint, I'm going to skip that part. Okay, so because this orbit belongs to some sort of a compact set, we're going to call that attractor is a compact attractor. Okay, so that's why the title is a compact attractor of the NRS. Okay, and so what tau did is in very high dimension, d greater than or equal to 5. But it is because in higher dimension we have a very better dispersion equation. Okay, so for the linear solution, it is decaying in time with this rate, d over 2.
Also, large J depends on epsilon.
Oh yeah, sure. J is also dependent on epsilon.
J can be many.
Sure. Yeah.
Yeah.
For given epsilon, J is a finite number. Yeah. But the number of the J could go to the infinity as infinite epsilon goes to 0. Okay. So because of such a dispersion, if the dimension is higher, then we have a better decay. Okay. So because he used so-called double two-metric, then that works only for the dimension greater than or equal to 5. Okay? So to this direction, the problem in lower dimension, the most interestingly, when dimension is 3, well, to approach it to KDB equation, we have to do that when dimension is 1. But that case is also widely open. And then such a property is also expected to be true for other dispersive equations such as the Klein-Gordon equations. Okay, so this is a second approach to the nonlinear the Soliton resolution conjecture. So yeah, this is it from it. Thank you.